Now this is a heavy one and perhaps not that exciting. Going to be here all week. God, Dave Jones doesn't have this problem. Have you seen the way he gets through his mailbag videos? You know, he goes through about 10 items in a minute, and I've just been waffling on about 2 things for the last half hour. God, the man is a master, isn't he? It's just me that's full of verbal diarrhea. Ugh, this is actually quite heavy. Oh, this weighs a ton. Oh, right, okay. I'm afraid part of these are off camera. So what these are is, I've only bought 2 at the moment, but we're actually going to need 6 of them. So you saw the Delta printer in action. So what you actually had is you had a carriage which was going up and down, and that carriage was attached to some arms, and those arms were attached to what they call the end effector, or maybe the hot end, the thing that did the 3D printing. So basically what we're going to need is, we're going to need 3 ball screws which we've bought, and we're going to have to manufacture some kind of slide. So unfortunately they've not arrived yet, they'll be in the next mailbag. What we've actually got is, we've got these rods, this is what I've bought, and this is 16mm silver steel, and this is heavy, it's a heavy bar, that. And it's precision ground, and again, quite expensive stuff. I think this was £20 a bar, and we're going to be using 6 of these. And I've also got some linear bearings, which they've not arrived yet. I was really hoping they'd be here. So we're going to have a linear bearing on this rail, a linear bearing on this rail, and that's going to basically connect to this nut. And then let's call that assembly a carriage. And then what we're going to do is, we're going to spin this ball screw with the stepper motor, and the carriage is going to shoot up and down there. Now I'm hoping that these 16mm rods, I'm hoping that they're going to be big enough and heavy enough to actually support the top of the 3D printer, because I was actually trying to decide where to put the stepper motor, and although in many ways it makes more sense to put the stepper motor at the bottom, because you can probably anchor it better at the bottom. The thing about putting it at the top end is that you saw the way the long arms stuck down. Let me move the camera over here a bit. So we're going to have a carriage that can shoot up and down to the top end, but the arms are going to hang down to the carriage to the base of the 3D printer. So because of the way that this screw is arranged, it's not full length. If I'd have bought a full length screw, that would have been even more expensive, because you would never actually use the bottom end of the screw travel, because the printer's got these long arms that stick down on it. So I think the stepper motors are going to have to go to the top, which in some ways isn't ideal, because again, we're going to get angular motion and torque, and when this thing is shooting up and down, it's also trying to twist the stepper motors, so it might make the top of the assembly twist, and it might vibrate and cause problems. We're going to suck it and see. I think I've actually massively over-engineered this. But c'est la vie. I think it'd just be interesting to check these. Now I'm expecting these to be precision, to be bang on 16mm, so I'd quite like to check that. Right, and I'm getting on there, I'm getting 15.98 3mm. I'm just wiping that over, there's just a little bit of drag. I'm just going to mic up, let's try, so that was 15.983, let's just try another section. That's 15.983 again. And I'm just going to go to the far end now, and that's 15.983 again. So it appears to be, on diameter, it appears to be spot on. It doesn't vary at all with the capabilities of my measuring equipment. Now the other thing that I would like to check is if the rods, and we've got 2 of them here, if the rods are dead straight. In the way that you would do that, or the way I would do it if I was at work, when I used to work at a mechanical company, we used to have some big flat granite tables or some big cast iron ones. And basically, all you need to do is you just put the rods on the table and you just roll them backwards and forwards with your hands like that. And if they're not dead straight, even the tiniest amount, you could actually feel it. They would actually, you know, they would go up and down if they were slightly eccentric. I can't do that on here. It's not particularly flat. I've got a rubber mat on it, and the bench itself isn't particularly flat either. So we can't do that. So we're just going to have to take it as read that these are dead straight, aren't we? Now it's a shame that we haven't got those linear bearings. I really wanted to show you them. You'd probably make a lot more sense of what I was trying to do if you could see them. Let's put these away, and we'll see them again in the future. Well, I suppose I'm going to have to speed things up a bit, aren't I? Because I'm sure you guys and girls have got, you know, beer to drink and good stuff like that. Linear guides. I didn't think they'd arrived. Oh, got lots of things here. Just put them bloody rods away. We'll get them out of here. So what we've got here is a selection of, well, these three. These are linear guides, and I've actually got 3 of them here. They're not very expensive. They're only a few pounds a piece. And I've actually got 3 of them because I couldn't really decide which type I was going to go for. I think the specification from is probably the same. It's just the mounting detail. So let's get them all out. You just missed a good bit of comedy there, by the way. This scalpel I'm using just rolled off the bench and managed to embed itself in my foot because I'm wearing bedroom slippers. So that was really quite entertaining. Here we've got, this is what they call a linear bearing. Okay, so if you look inside there, there's actually some ball bearings. And what these are going to do is they're going to run up and down these steel rods. Now, I'm sorry the camera handles and things aren't very good on this today, but bear in mind these long rods are more than 1 metre in length, so I can't get it all on camera, so I'm sorry about that. So what I was trying to explain earlier is we've got the nuts here, and if we just rotated this screw, the nut would actually spin round, so we have to stop it spinning. So what we're going to actually do is we're going to build a platform across here, which is it's going to pick up the slide. It's going to be bolted to this nut, and it's also going to be bolted to this other linear bearing at the other side. So that basically means when this nut rotates, when the screw rotates rather than the nut rotating, what it will actually do is it will move up and down, and it'll be guided by these bearings here. So we need to actually build I think probably the best thing to call it, if it was a lathe, I think we'd call it a carriage. So we need to build a carriage which takes in the nut and these two linear bearings, and effectively all it will be is a big flat plate with some holes in it which we can bolt these onto. And then on top of that flat plate we're going to have to somehow tether it to those long arms that we're pointing down. Now I bought 2 types of linear bearing, I think I said earlier, and there's really no difference in them apart from just the mounting hole. Everything's covered in grease. So yeah, the bearing, I think it's effectively the same bearing, it's the same size. Let me just slip that one on so you can see that one. Oh, in fact, let me... So we've got a choice of using a bearing that's got, well, basically 4 holes drilled around the circumference, and they're just clearance holes. They're not tapped or anything like that. Probably would have been handy if they had been tapped, but they're not. They're just clearance hole to put a nut and bolt through. So what we'll do is we will bolt our saddle plate. Our saddle plate is probably the best thing to call it. We're going to bolt that saddle plate to the nut and to the other bearing, and so I can either use this bearing that's kind of round at this end, and we can either use that, or we can use this one. And as far as I can tell, I think it's exactly the same bearing. It's just a different style of mounting. I don't know if there's an advantage to use a round mounting like this. I don't know if there'd be any advantage at all. just take that off. There you go, sorry, can you see that? Hopefully you can see that a bit more clearly now. So one of them has got this round mounting, you know, it's got holes drilled around the circumference of it, and this one has just got the four holes in a rectangular pattern. I don't know if one's more an advantage to the other. I guess one thing is that we'll be able to actually have a smaller saddle if we don't have to stick out so far sideways, because that was kind of my thought, is that we can probably squeeze all these things up quite close together. So we can actually squeeze these together in a much tighter spacing than if we was to use this type of linear bearing, because these just take up less space because they've got the edges cut away. Would that be an advantage or a disadvantage? I don't know. I think from the point of view of making the machine rigid, there's probably some advantage to spacing these off a little bit further apart anyway. Not exactly sure on what geometry we're going to go for. So again, if you guys have got any thoughts or ideas about that, let us know. So here's another item that I've bought, and this is basically just some collars, and these should be about the same thickness as the same diameter, sorry, as these silver steel rods. So in theory these will fit on here. I don't know if we'll be able to get one on. Let's try it. So basically we've got these clamps here, and they've got an Allen screw in them, so you can tighten them up, and they're not going to slide on the rod. Well, we can slide them up to where we want them, and then you tighten up this Allen screw here, and they will grab the rod and they won't move anymore. So again, what I was thinking that we will do is we'll make a plate that goes from this clamp to this clamp, and it will pick up this bearing carrier for the bottom of the screw. So that will hold this bottom bearing in a precise location. So hopefully it's coming together. I'm sorry you're not getting to see all of it, because from the camera angles I can't lay it all out on the bench so you can see it, so you're only seeing little bits of it here. And what I thought I would do is I'm going to try and build up one side first. There's going to be 3 sides to it in these Delta printers, and I bought 3 of the screws, but regarding the other parts I've just bought enough to build up one side. So this is one side, and we need to build 3 sides in total. So what I thought we could do is we can just build up one side of the Delta printer, and in the words of my favourite Canadian, we will see if it'll chooch. Now the mailbag still isn't empty. Got a few more items to go. Well, I'm very much hoping that we're down to our last few items now. Yeah, as you can see, it really was somewhat of an alcohol-fueled buying spree. So yeah, I'm not too proud of myself. Okay, here's our mystery item. Does anybody know what this is? Let me just rotate it round so you can get a better look at it. Let's have a look from one end at the other. And is that tight? We've got some screw threads on here, so we can adjust. It looks as though we can adjust this. We can move these pieces of metal up or down. Anybody got any ideas? Okay, well, some of you will know what this is. What this is, it's an adjustable reamer. And what's a reamer, you ask yourselves? Well, you actually use it for, if I was to say you use it to enlarge holes, it would be partly true. What you actually use a reamer for is to set a hole to really the correct size. If you actually drill a hole in a piece of metal using a twist drill, I mean, most of us look at that hole and we say, oh yeah, it's a round hole. But it actually won't be perfectly round. It'll have a lot of imperfections in it due to the way that the drill is ground, but also due to the way that the drill fits into your chuck and something called run out. If you typically drill a hole, I don't know, let's call it a 15mm drill. If you actually drill use a 15mm drill in a piece of metal, you don't get a 15mm hole. You'll almost certainly get something just under, or much more likely you're going to get something that's just a little bit over. Now, it usually doesn't matter. It certainly doesn't matter if you're dealing with woodwork, in that there's a little bit of give in the material. But if you're actually drilling holes in metal and you need to do very precise holes, what you actually have to do is you have to drill them in kind of 2 stages. Now, I've bought this to drill the holes for. You saw the precision ground rod that we had earlier, and I think that was about bang on. Well, was it 15.982mm or something like that. It was 16mm rod, but it was very, very slightly 0.007 under. So if you wanted to drill a precise hole for that rod to go through, what you would probably do is you will drill the hole undersize. So rather than drilling a 16mm hole, you'd probably drill, and I'm guessing now, 15.8mm, and then you would finish the hole using a reamer. So these bright parts of the metal here that you can see, I'm being careful when I touch them because they are razor sharp. These are made from high-speed steel, and they're cutting blades. So what you do is you drill the hole, and then you put the reamer into it, and you put a tap wrench on the end of it. You saw me using a tap wrench in the Christmas tree repair video. You put a tap wrench on the old of it, and like using a tap, you put this into the hole and you rotate it using some oil on it. You've got to keep it lubricated. Now, you can buy lots of these reamers, and a lot of them will be set to a particular size. So you'll buy a 15 or a 15.5. You know, they're a set size reamer, but the thing about this reamer is it's on a taper. So basically what you can do is you can expand it, you can make it a little bit bigger. Now, you can only make it a tiny amount bigger. I think the adjustment on this reamer is about 0.5 millimeter. So it goes from just under, I think it's something like 15.5 millimeters to, I think it's just slightly over 16. So it's quite a small adjustment range, but you can adjust it. So you drill the hole, you ream it. If you want to make the hole very slightly bigger, what you do is you adjust these 2 collars. There's a collar there, there's a collar there. You actually screw it this way, you screw it down, and these blades are on a taper, and they'll open out a little bit, and they will cut the hole slightly deeper. So I bought that to use on this project because I didn't have any good reamers. Most of my reamers I've stolen from work over the years, and you know, they were in a box. We don't do any machining at work. We haven't done any machining for many years, but we used to. So we had a big box of old reamers, but what we did at work was big stuff. So, you know, it was like over 1 inch and above. Really too big for me, but I couldn't see them being thrown away, so I brought them all home with me. But I don't have any small reamers, and I don't really have any metric ones. So I bought this small adjustable reamer to use. Okay, so I've got the final item of the day here, and again we're going to have another impromptu pop quiz to see if anybody know what these are. So you can see we've got a set of them here, and I'm going to get one out and let you have a look at it, and you can see if you can guess what it's for. So we've actually got a set here, and here's one to look at, and it's a big T-shape. So again, a pop quiz. Does anybody know what that is? Let me try and give you some hints. Well, what I can do with it is we've got these 2 arms that stick out here. We've got a handle with a knurled finish. We've got a bit that turns at the bottom. Just turn that, you see that? Spin it. And that's a big one. Let me find a small one that's a bit easier to handle. And we've got 2 arms that stick out on either side, very much like a T shape. It's got a shaft on it, knurled, and it's got a little knob at the bottom which turns. And what we can do is we can squeeze these like this. You see they're on springs, they're kind of plungers, they'll go in and out. So what you can find is if I just squeeze these arms in now, and I'm just going to tighten up this bottom screw and let go, you see the arms have stayed in there. And if I just turn the knob, I can release them. See, they shot out again. Let's push them in, adjust the knob, stayed in, just release it. So any ideas what you use that for? Come on, place your bets. So as you saw earlier, we've got a set of these and they're all slightly different sizes. Well, I've just been rummaging around in the garage again and I found this lump of metal, and what this is well, it was a hydraulic cylinder. It was part of an hydraulic cylinder off an old press, and I think this press was being used to pull wheels off locomotive axles. That's what it was used for, and it was an old Imperial thing, and they were throwing it in the skip at work, and I thought, well, it has some precision machining on it and hydraulics and various things, so I couldn't see it being thrown away. So I actually thought, well, I'll have that and various other bits, because it's got a lovely machined internal bore. This is a hydraulic cylinder, so inside of it the machine finish is beautiful. It's a mirror polished finish, because this would have been machined out and then it would have been honed. So it's got, like I say, if you put your finger in here, there's no imperfections. It just feels like glass. So if we wanted to measure the inside of this, how could we do it? Well, we could use a pair of calipers like that, and try and look at it. And again, I'm afraid I'm not lined up with it. You've got a better view than I have. So to me, that's looking about 40.3 millimeters. So you could do that, but that'd be a pretty rubbish way of doing it, wouldn't it? The more intelligent way might be to use these internal jaws. I think it's going to be easier if I hold this up. I'm afraid I can't do it so you can see and I can see. It's just difficult to hold. 39.99. So I was really suspecting that this would have been Imperial, but it's obviously not. It's metric. I wonder if this piece of equipment was originally manufactured abroad. I don't know. 39.96. Well, so we're getting some measurements off there, but the thing about this type of caliper is they're not amazingly accurate. I mean, they do go to 2 decimal places, but they're just not super accurate. As we've discussed in the past, if you want to do really accurate measurements, what you need to use is a micrometer. So let's get the micrometer out. And we've immediately got some problems in that the micrometer is designed to measure, the outside of something. It's not designed to do the inside. Now, the second problem I've immediately got without even starting is that this micrometer is not big enough, is it? Well, there was a fly in my ointment. Bugger. Didn't see that coming. Oops, minor cock up. We'll edit that out later. So I've been out in the garage and I've got this old micrometer, which is much bigger, and it's not one that I've actually used before. It was actually given to me by somebody at work who was retiring quite a few years ago, and it's got the initials PF etched into it here. So yeah, that was Pete. So thanks very much, Pete. You let me have this when he retired. He was one of the machinists where I worked. Depending on what size you want to measure, it's got different length anvils to install, because this bit's only got so much adjustability, and that's about 1 inch of adjustment maybe. So if you want to measure something really big, you take the long anvil out and you put a smaller one in. These, I think, because of this sliding arrangement, these adjustable anvils, they're not quite as accurate as maybe a fixed micrometer, but yeah, good enough for me, better than what I need. Although I was using a little bit of WD-40 a second ago as a cleaner, I try to avoid putting oil and stuff on measuring equipment because it does attract grit, and it doesn't really need it. So I think stuff like IPA is probably a better idea. I do occasionally put some very light, and it is very light. I have some sewing machine oil which is very thin, and I do occasionally put a little drop of that on it. So whenever you've changed the anvils on one of these micrometers, they come with a series of test bars, because what you have to do is you've just got to recheck the zero on them, So at the moment this has, I think it's got a 0 to 2 inch range. So what we actually need to do is we need to check the 0 on a 1 inch test block. So what we'll do that, we'll just again we'll just give this a wipe. What I tend to do is I do give these a bit of clean with some solvent, some IPA or something like that. But before I put them away, I do give them a little smear of light oil. The problem with a lot of my test gear is I'm not careful, it goes a bit rusty in the garage because I just don't use it frequently enough to keep it in good condition. And I was actually thinking that today when I got some of it out of the garage. I thought maybe I'm going to stop keeping this stuff in the garage because the humidity, the moisture in the air and the variance in temperature, it's probably not very good for it. Promotes rust, and that's the last thing you want. Okay, so we've wiped the crud off that. So hopefully we're going to get a 0 reading on this now. So I'll put it in there, put my test piece in, and I'm not going to use the clicker on the end, I prefer to feel it. Bang on 0. So yeah, happy with that. So let's have a go with our telescoping gauges. I'm going to put that inside, let it flick out, give it a little bit of a rock from side to side just to allow the anvils in the gauge to centre. Now this is the tricky bit. So in theory now, this distance across here should exactly match the bore size. In theory, but this is all about feel. That's what machinists call it, having the feel of it. Okay, so we need to open this up a bit, don't we? So let's give that an open. A bit tricky to do because it's quite a big micrometer. It'd be nice if I had a micrometer stand. And you see the people who are proper machinists, what they do is they hold the micrometer in one hand like that, and then they turn this with one of the fingers, but it's actually yeah, it's a bit fiddly. And what you're trying to get is you're trying to get the same feel, the same drag between the anvils of the micrometer as you've had with the telescoping gauge. That's why they call it the feel. I'm trying to get the same feel for it as I did when I was in the inside the bore. So it's really not easy to do. Right, let's see if we can just read this off. Now, I don't use these very often, and they are all slightly different the way they read, just depending on how the way the graticule is set up. I've never read this one before, so we'll have a go at it, and I might get it wrong. So basically, this starts at just over an inch. Well, it's an inch. So the first measurement is going to be an inch. We're at 1 inch to start with. Then we've got to add the second number here, which is going to be 5. Let me see if you can see that. So the next part of the measurement is here. It's the 5. So I'll write that down there, 5. And then basically we've got to count the small divisions next, and each of those is 25 thou. So it's the 5 plus 25, 50, 75. So the final part of the reading here is on the circumference, which is, I don't know, 1, 2, just 2, isn't it? Plus 2 thou. So got to add to our 5 there, 75, we've got to have 2. And it's actually about halfway between them, so let's call it 2, 5. So if I just write that down, 1.57, 2 to 5 is 7, and then the final one, 5. So I'm calling that 1.577, that's a 7, sorry, 5 inches. So let's see, let's convert that into millimetres, shall we? So in inches we measured, let's put a number in, 1 point, where's it gone? 5775. 5775. Is that right? Yep. Which gives us 40.0685 millimeters. Now, problem is, I don't know if that's right or wrong. It's certainly in the ballpark. We'll just try and double check that using the calipers, but you've got to remember this is only a rough check. In theory, the micrometer is a much better, much more accurate reading. 40.03. So, yeah, a little bit of variance there. You can see it gets hard, doesn't it? As always, thanks very much for watching. Bye for now. It's cool.